Hello my friends and welcome to this new practical activity on support vector machines for classification, of course. Alright, so we already built two classification models, Logistic Regression and KNN. We got the best results so far with KNN, and now let's see if SVM can beat it, or even the one after that, kernel SVM. Alright, so before we start, as usual, let's make sure everyone here is on the same page. Right before this tutorial, I gave you the link to this whole folder, so make sure to connect to that link, and if that's the case, then follow me into part 3, classification, and then section 16, support vector machine SVM. And we're going to start with Python, of course, as usual, and in this Python folder you will get two files. The first is the same dataset social network ads.csv containing 400 observations, where each observation is actually a customer who bought, yes or no, a SUV that is advertised on social networks. And for each of these customers you have the age, the estimated salary. So these are the two features, and with these two features you will predict the dependent variable purchased, meaning whether or not the customers bought the SUV. So 1 means yes, the customer bought a previous SUV, and 0 means no, the customer didn't buy any SUV. Alright, so same data set, and of course the second file is this support vector machine implementation in the IPYNB format, which you can either open with Google Collaboratory or Jupyter Notebook. And as far as I'm concerned, I'm going to open it with Google Collaboratory, but feel free to choose your favorite IDE. Alright, so let's put that file here, actually here, and right now it is loading the notebook, laying it out, and in a second we should have it open. There we go. Alright, so that's the whole support vector machine implementation, and of course it is exactly the same as before. In order to re-implement this, we will only have to change the code cell where we build and train this model, because indeed this implementation results from the exact same classification template that we made when we built the logistic regression model. We saw clearly when implementing the k-nearest neighbors model how indeed we only had to change one cell, and how this template worked super well for that model. So here for SVM we're going to do exactly the same. We're just going to leave all the cells as they are, as they actually were in the logistic regression model, and we will only re-implement the cell where we built the SVM. Alright, so let's do this. Let's create a new copy of this file, because this file is in read-only mode. So let's click here, save a copy in Drive, and this will create a copy inside which we will indeed be able to modify the implementation and mostly to re-implement that code cell to build the SVM model. Alright, perfect. So at the beginning, of course, we start with the data preprocessing phase with all the same outputs displayed on the notebook. So that's all good. Then we apply feature scaling, because you know it improves the training performance, and anyway it's never bad to apply feature scaling. And finally, there we go, that's the cell we have to re-implement together, because indeed it is the one that differs with respect to the previous implementations. So let's click this trash button here to re-implement it again. Let's create a new code cell, and now my friends, over to you. Once again, I would like you to please press pause on the video and try to implement that code cell yourself. And that's because I not only want to train you in machine learning, but also train you on how to be independent with machine learning. So right now, the exercise I want you to do is to do some research in the scikit-learn API to figure out which class allows to build the SVM model. So you will find it very easily actually, because there is no trap in the name of the class or the name of the module. So I trust you will totally be able to do this exercise successfully, and mostly know which method to use at the end to train that SVM model on the training set. Alright, so please press pause, and now in 2 seconds I'm going to give you the solution. Alright, let's do this. So I already have the scikit-learn API opened. That was for the nearest neighbors, the k-nearest neighbors, which we implemented previously in the previous section. We used this class, k-neighbors classifier, and now the next thing we would like to find in this API documentation is the module that contains the class that allows to build the SVM model. So naturally, where could we find it? Here, should we scroll back up or scroll down? Well, let's hope that, the name of the module starts with an S, because here, the modules are organized by alphabetical order. So since here we are at n, nearest neighbors, let's hope that the name of the module we're looking for starts with an S, like support vector machine. So let's scroll down and random projections, semi-supervised learning, and there we go, support vector machines, hello. That's exactly what we were looking for, support vector machine. So that's not the name of the module. The name of the module is SVM, but same, that stands for support vector machines. All right, and then, well, the hardest part is done. Now, according to you, which estimators, because here you have all the basically support vector machines-based machine learning models. And so according to you, which one do we need to take here? Well, we actually have two options. We could either take the linear SVC, which will directly build the linear support vector machine model, or we can take this one, SVC, and choose a linear kernel. All right, and we will actually go for this option because in the next section we will study the kernel SVM models, which, as you might guess, allow us to choose some different kernels in our SVM, including the linear one and the non-linear ones, like, for example, the very famous one, RBF, right? Radial basis function, which is actually the one we used in SVR. That's the class, you recognize it, that we used to build the SVR model in the part 2 regression. All right, so there we go, let's go inside, and here is the name of the module, SVM of course, and the class that we must now import in order to build our SVM model. All right, so let's start with this as usual. Let's get, this path and let's adapt it inside our code cell. You know how to do this. We need to start with from. So from the scikit-learn library and then the SVM module of the scikit-learn library, we will import the SVC class. Okay, so that's the first step. And then the next natural step, you know it by heart, it is of course to create an object of this class. And we need to keep here the name classifier because in order to not have anything to change afterwards, so classifier, which will be nothing else than the SVM model itself. And so to create such an object, we need to call this class, well, I can just type it, SVC, and then add some parentheses. And now the question is, what do we need to input here as parameters? Well, I hope you have the reflex to think, of course, we need to input the kernel, because as I've just explained, this SVC class allows to build kernel SVM models with either a linear kernel, which is the classic SVM model, or a nonlinear kernel. So here in our parameters, we'll have to specify that we want a linear kernel because we're starting with the classic SVM model. And then in the next section, on kernel SVM, we'll choose a nonlinear kernel like RBF or polynomial, we'll see. But there you go, that's our first argument. And indeed, when we have a look at the documentation, we can see that indeed the second parameter here is kernel. And the default value is RBF, so we'll have to specify that we want linear to start with. And then, as you can see, you have many other arguments, parameters, and you can check out the description for each of them. But no worries, we won't change their default value. We'll just keep their default value, like for example, the regularization parameter for which we'll keep the default value of 1. That's fine. You'll see in the visualization that there is not much we can do in order to improve the model or to avoid overfitting. So there we go. The only parameter that we'll take is this one. Kernel equals not RBF, but linear. All right, so let's do this. Kernel equals, in quotes, linear. All right. And then, I know I've just said that we won't have to input any other parameters, but let's add anyway, this one, the random state parameter, and set it equal to 0, just to make sure that we get the same results displayed on our notebook, because there are some random factors when we build this SVM model, and therefore for teaching purposes, it's better if we all have the same results displayed in our notebook. All right? And that's it. Congratulations, that builds the SVM model, the classic one with a linear kernel, and now you know how to finish this. Of course, our last step here is to take our classifier from which we're going to call the fit method to train our SVM classifier on the training set. And we have to input that here in two parts. First, the matrix of features of the training set, which is x train, and then the dependent variable vector of the training set, which is y train. All right, so you know this perfectly well now. It's like your native language, right? Okay, I hope I'm right, but there you go. Congratulations. This implementation is now over thanks to this very efficient code template. And so now, well, we'll just run everything and observe the final results in the end. All right, so let's do this. Let's not forget to, import the dataset here, upload it in the notebook. So click this folder here. Then you will have to wait a few seconds because your notebook will be connecting to a runtime to enable file browsing. And in a second, we should see, there we go, the upload button. So we're going to click that. And well, that's the dataset, but I'll show you the whole path again. So you find your machine learning A to Z folder, codes and datasets, which you could download in the previous tutorial in the article. Then you're going to go to part 3, classification, then to section 16, support vector machine, and Python, and social network ads.csv. You click open, and this will upload the dataset inside the notebook. There we go. And now you can run all the cells by clicking runtime here, and then, are you ready? Run all, and this will run all the cells. And perfect, now we have our SVM model with a linear kernel with all the default values of the parameters here except this one, linear kernel. And so there we go, then we have the rest of the cells. When we predict the new result, indeed we get the right prediction. Remember, it's 0 for that particular first customer of the test set of age 30 and estimated salary $87,000. Indeed, it is predicted not to buy the SUV as it is the case in reality. Okay. Then when we predict the test set results, once again we see that we have many correct predictions except some of them. This one, and this one. Okay, but it looks very good. However, what we're mostly interested in, and we're about to get it right now, is to see the accuracy on the test set. The number of correct predictions, or if you want, the number of incorrect predictions. Are you ready? We're about to get it right now. Right? That code cell prints the confusion matrix and display the accuracy. And wow, okay, interesting. So it beat actually the logistic regression model, right? Remember, the logistic regression model had an accuracy of 89%. And here the SVM slightly beats it by 1%. However, it does not beat the KNN model, which remember had an accuracy of 93%. All right, so it doesn't beat it. And now we're actually going to understand why. Why didn't the SVM model beat the KNN? Okay, so we'll actually figure that out in a bit, or actually, I can just show it to you here on the original implementation of the SVM, but you're gonna understand now why it didn't beat it. Well, there you go, it didn't beat it because once again, since we chose a linear kernel, well, the prediction boundary, or the decision boundary, is actually once again a straight line, and therefore even if you rotate it either this way or this way, well, it won't be able to catch the right predictions for these green customers here, which should belong to the green regions. And same for this one. If we rotate it this way, well, we will catch these ones, but then we will catch more incorrect predictions around here. And if we rotate this way, from here to here, well, indeed we will catch these ones in the right prediction region, but we will get more incorrect ones here. So that's the problem of linear models here. Indeed, it's much better to have a prediction boundary that does some kind of a curve here in order to catch only the red customers who should be predicted not to buy the SUV and leave the green ones in the green region. All right, that's exactly what we got with our K nearest neighbors, right? It is not a smooth curve, but it did the job of selecting the right red customers here, still leaving some green ones, but here catching the right green ones in the right region, the green region. And here, of course, since we have this straight line, it's impossible to do. But no worries, I'm sure you have the intuition that once we use a nonlinear kernel, well, we'll be able to catch the right green observations here in the right green region. And well, that's exactly what we'll find out in the next section when implementing the kernel SVM model. All right, so let's see if we're done here. Yes, we are. So it finished to execute. And of course, we get the same results. And let's see for the test set, still running, oh, wow, okay, so funny timing. It just populated here. And well, still the same. Because of this straight line here, well, we have some green customers, customers who bought in reality the new SUV, but couldn't be predicted correctly because they fall in the wrong region because of this prediction boundary that cannot separate well our two classes. All right, so same problem, and you might guess that this problem will be fixed once we choose a nonlinear kernel for our support vector machine model. All right, so let's find out about this in the next section on kernel SVM, and until then, enjoy machine learning.